Hey there. We're going to go over some incline forces notes. Now, up to this point, all the situations that we've looked at, it's been an object that's been on a horizontal surface. So for instance, here's a box and let's say we're pulling it to the right with a rope and there was some friction involved and we know the Fg goes straight down and then the normal force goes straight up. And then from there, we were able to use Newton's second law and calculate the acceleration of this object. And now we're going to get into situations where the object is on an inclined plane. So let's say we have a ramp here, and on the ramp we have a box, and the ramp is at some angle theta with the horizontal. Now we've drawn free body diagrams in this situation. Let's say that we have the box being pulled up by some rope tension, and then we have some friction involved. And then we know our weight goes straight down and the normal force goes perpendicular to my surface. So the free body diagram would look something like this. Now we have one or two options of what we can do here. The first is we can keep our x and y axis how we normally do. Say this is y and then here is x. Now if we do that, let's kind of draw in our x and y axis. It would look something like this. And looking at that, we have, let me switch back to our black. And let's count all the ones that we have at an angle. Tension is at an angle, and my normal force is at an angle, and then my friction is at an angle. So we have three forces that are at an angle that we would have to break down into our x and y components. Now we have an alternative to this. Let's redraw this. We have our ramp. There we go. And here's the angle. Here's our box. And let's draw the same forces. We have tension and we have friction. Fg straight down. And then the normal force perpendicular. And what we can do here is we can shift our x and y axis. And we shift it to where it looks something like this. So here is my y and here is my x. And let's go ahead and draw in that x and y again. And it would look something like this. And so now let's go in and let's count how many we have that are at an angle. And we only have one, and it's FG. So by shifting our x and y axis, we can make it a lot easier on us so that we don't have to resolve so many vectors into the x and y components. And what we end up with is we have FG straight down, and then we have our FGY and FGX that we have to end up solving for, which is much easier than breaking the tension, the normal force, and the friction into x and y components. And so the next thing we need to kind of look at is what is this angle that we're going to be working with. So let's kind of expand this again. So there's the ramp, and we have the box on the ramp. Kind of make our horizontal surface there. And we know FG goes straight down. And if we call this angle here theta 1, now we know we have a right angle right here. And we'll draw in our new y-axis that we shifted. And let's call this theta 2. So looking at this first little triangle right here, we know that theta 1 plus theta 2 would have to equal 90 degrees, right? Because this is a 90-degree angle here. And let's switch colors now. And let's look at this triangle. So this triangle, we have a 90-degree angle right here. And let's call this angle from here to here theta 3. And so based off of that triangle, theta 2 plus theta 3 has to equal 90 degrees. And what we can draw from that is that our theta 1 has to equal my theta 3. So typically the problem will give you this angle here, the angle that the ramp makes with the horizontal. And then that ends up being my angle here that we can resolve our x and y components of FG. So let's kind of see what this looks like in a couple problems. So this one here, it says we have a 2-kilogram box. It's at rest. There's one of those important words. We'll underline it. And it makes a 37-degree angle with the horizontal. And they're wanting us to find all the forces. So let's first draw our ramp. There's our ramp. Here's our theta, and it's equal to 37 degrees. Here's our box. Our box is at rest. And so then we'll draw our free body diagram. We have FG going straight down. We have the normal force that's perpendicular to the ramp. And there has to be some friction there to prevent this thing from sliding down the ramp. So that friction will go up the ramp, and that'll be static friction because the object's at rest. And so they want us to find all the forces, so we need to find Fg, the normal force, and that static friction. So let's start out with our Fg. We know the mass is equal to 2 kilograms, and we know our Fg equals mg. So that gives me 2 kilograms times 10 newtons per kilogram. So your Fg is equal to 20 newtons. So there's one. Now we need to find our normal force and our static friction. So to do this, let's start out by making our net force equations. So again, my y is going to be like this, and my x is going to be like this. We're going to shift our axes. So I'll draw in some dotted lines here. So that's going to be your y, and then your x. So my net force equation in the x direction is going to be that friction, that static friction, minus the x component of Fg, and that's going to equal 0 because it's at rest. And my net force in the y direction is going to be the normal force minus Fgy, and again it's going to equal 0 because the object's at rest. And so what we can draw from these two equations, using this net force in the x direction, we know that the friction is just going to be equal to Fgx. And from the y, we know that the normal force is going to equal Fgy. So what we have to do is just resolve the Fg into our x and y components, and that will tell us those other two forces. So if we expand that a little bit and draw out our triangle, we have Fg right here, and here's Fgx, or I'm sorry, Fgy, and FGX. And this angle here is 37 degrees. So let's start with our y component. So our y component is adjacent with that 37-degree angle, and the FG is your hypotenuse. So we're going to use a cosine function. So cosine 37 degrees is going to equal FGY over FG. So my y component is going to equal FG, which we found earlier was 20 newtons. So 20 newtons times cosine 37 degrees. And if you punch that in, you should end up with 16 newtons. So the y component is equal to the normal force, which is equal to 16 newtons. So there's two forces. Now we just need to find our static friction, and that is going to be equal to the x component of our FG. So we'll use the sine function. So sine 37 degrees is going to equal our x component over FG. So my x component is going to equal 20 newtons times sine 37 degrees. And if I plug that in, you should end up with 12 newtons. So the x component equals my static friction, and that equals 12 newtons. So now we have found all of those forces on this box. Now let's look at another example where we also are going to have some acceleration involved. So this one says we have a 50-kilogram box. It's being pulled up a ramp by a cable. The ramp makes a 37-degree angle with the horizontal. Tension is 600 newtons, friction is 200 newtons. And we're going to do two things. We're going to find all the forces, all the remaining forces, and then calculate the acceleration of the box. So let's start out by making our ramp. And we have a box that's being pulled up, so we have tension here. FG goes down. Normal force is going to be perpendicular, and then we're also going to have that kinetic friction going this way. And so the problem gave me the tension, and they gave me the friction, so we need to find our normal force and then the weight. So let's start out by finding the weight. So the mass is equal to 50 kilograms. So the weight is going to equal 500 newtons. So we found our weight. Now we just need to find the normal force. So let's draw in real quick our x and y axis. Remember, we're going to shift it, so it's going to look something like that. And then let's make our net force equation. So the net force and the y, we're going to have the normal force. So Fn minus our Fgy. And that's going to equal 0 because it's not accelerating off of the ramp, it's accelerating up the ramp. And so the normal force is just going to equal your y component, so Fgy. So let's make our triangle over here. So we have Fg going here. We have Fgy here and Fgx. And the angle is 37 degrees, right? Because our angle here is 37 degrees. So to find the y component, we're going to use our cosine function because it's adjacent with that 37-degree angle. So cosine 37 degrees is going to equal Fgy over Fg. So the y component is going to equal 500 newtons times cosine 37 degrees. And when you punch that in, you end up with 399 newtons. So the y component is equal to normal force, which equals 399 newtons. So we found all the forces, or the remaining forces. Now the problem wants me to find the acceleration. So to find the acceleration, we're going to use Newton's second law. It says that acceleration is equal to the net force divided by the mass of the object. So we need to find our net force. And the one that we're interested in is in the x direction, right? Because we're accelerating up the ramp. So let's make our net force equation for the x direction. And so we're going to have the net force in the x direction is equal to tension minus, you have that friction, kinetic friction, but we also have the FGX. And now it's not going to equal 0 because it's accelerating. And so to find my net force, we need tension, which we already have. We need the kinetic friction, we have that, but we don't have the x component of our FG. So let's find that real quick. And we're going to use the sine function of our triangle over here. So sine 37 degrees is equal to the x component over FG. So your x component is going to equal 500 newtons times sine 37 degrees. And when you punch that in, you end up with about 301 newtons. So now we also know our FGX. So we can solve for our net force. So net force in the x direction is going to equal tension, which the problem told me was equal to 600 newtons, minus friction, which it said was 200 newtons, minus what we found over there for our FGX, which was 301 newtons. So your net force in the x direction is just going to equal 99 newtons. So to use this equation for Newton's second law, we need the net force. Now we have it. We also needed the mass, and the problem gave us that. So now we can find the acceleration. So the acceleration is going to equal 99 newtons divided by, make sure you use a mass here, 50 kilograms, which is roughly 2 meters per second squared, and that would be up the ramp. So when we have these problems that are or has an object that's on an inclined plane, we always want to shift our x and y axis, okay, so that we end up just having to resolve one force instead of 2 or 3 forces. And it makes it a lot easier on us when we solve this. And so we end up just having to resolve our FG into those x and y components.